We're very happy to have Edward Witten talking now. Thank you, Ed.
Okay, thank you. So first of all, thanks very much for the invitation to this conference. And I'm glad to have the chance to speak. So I'm going to be explaining work with David Ayota, which hopefully will appear soon, where we're trying to understand a quantum field theory perspective on a picture that's been developed by Eddinghoff, Frankel, and Kazhdan about an analytic version of the geometric Langlands correspondence. There are various earlier developments, but the only one I'm citing here is the one that's most related to physics by Teschner. I have not attempted to provide math references. So in the gauge, I'm going to begin by reviewing the gauge theory approach to the traditional version of geometric Langlands. That'll be roughly the first half of the talk. And then in the second half of the talk, I'll explain how to adapt the construction to interpret in the same language the work of Eddinghoff et al. So in the gauge theory approach, the starting point for usual geometric Langlands is n equals 4 superamials theory in 4 dimensions with the gauge group G, or with the GNO dual group G dual. By the way, we're in the midst of the outbreak of the 17-year cicadas, and I'm closing a window because I suspect you're hearing a lot of cicadas from outside. I wonder if that reduced the background noise noticeably. So,
I think. Yeah.
Okay, the theory based on G has a gauge coupling constant E, a real parameter, and a topological angle theta, and they combine to a parameter tau, a complex parameter in the upper half plane. So there's an elementary symmetry of shifting tau by 1, which has to do with the fact that the incident number is integer valued. And similarly, the dual theory has an analogous parameter, T dual, also with an elementary symmetry. The claim of electromagnetic duality, which goes back to Montonen and Olive, is that the theories based on G and G dual are equivalent under tau going to -1 over tau, well, times this integer ng, which is it's 1 for simply placed G, and otherwise it can be 2 or 3. Now, this isn't particularly a statement about geometric Langlands, and people studying this duality are usually studying questions that have no obvious relation to geometric Langlands. But we can specialize to the situation that leads to geometric Langlands. To do that, first we consider a topological twist that leads to a CP1 family of topological field theories, parameterized by complex parameters psi or psi dual. If we study the whole family, then first we get this highly quantum equivalence under psi dual equals -1 over psi times the same integer n sub g. We also have these elementary symmetries. And this becomes the duality of what's called quantum geometric Langlands. But for today, we'll consider the basic duality between psi equals 0, which I'll call the A model for G, and psi dual equals infinity, which I'll call the B model for G dual. So what ingredients will we meet in this duality? In general, in quantum field theory, in dimension D, we associate a number to a D manifold, a vector space of physical states to a D-1 manifold, and a category of boundary conditions to a D-2 manifold. In the present context, though, although we'll be on a 4 manifold, we're only going to consider 4 manifolds of the form sigma times C, where C is a fixed oriented 2 manifold. Sigma will be some other 2 manifold. So effectively, we'll be doing topological field theory on sigma with C as a parameter. So that means that we'll have a category of boundary conditions in sigma that depend on C. So it's convenient to draw 2-dimensional pictures where I only draw sigma and not C. So here are a few pictures. A basic one is that sigma might have a boundary. In that case, to formulate quantum field theory on sigma, we need to specify a boundary condition. So that will be an object in the category of boundary conditions. Well, the reason boundary conditions make a category from this point of view is that if we're given 2 boundary conditions, then we can consider a strip. So we have a 1 manifold whose ends are on the 2 boundaries labeled by B1 and B2. It goes on in the future in the time direction. But remember, there's a vector space in codimension 1. In 2 dimensions, codimension 1 means a 1 manifold. In this case, an interval ending on the two boundaries. And if you like categories, you say that that vector space is Hom from B1 to B2. So again, there's a Riemann surface that's hidden in this picture. So everything in sight depends on a Riemann surface. So in particular, so does this Hom space. Now with this definition, Hom from B to B is an algebra for every B. So in this picture, we take two open strings ending on B on both ends, one here and one here, and they join together via this simple Riemann surface to make a single one. That's, in category theory, would be called multiplying two elements of Hom from B to B to make an element of Hom to B. So the picture is meant to explain why Hom from B to itself is an algebra. And moreover, although I haven't drawn the pictures, which would be the same picture with different labels, Hom from B to B prime is a left module for Hom from B prime to B prime, and so on. So electromagnetic duality will give an isomorphism between a category curly C associated to the Riemann surface C in the G theory at psi equals 0, and a dual category C dual associated to C in the dual theory at psi equals infinity. In addition, there's a natural mapping between certain natural functors on C and C dual. These functors come from what physicists call line operators. In a quantum field theory defined on a manifold M, a line operator is some sort of modification of the definition of the theory along an embedded one manifold K and M. The natural line operators at psi equals infinity are Wilson operators. A Wilson operator is the holonomy of a connection interpreted as an operator in quantum field theory. The natural line operators at psi equals 0 are the dual 't Hooft operators. So in physics, Wilson and 't Hooft operators are usually used to analyze questions like the confinement of quarks in atomic nuclei and other subtleties involving universality classes of quantum field theories. But for us, a line operator is a functor from the category of boundary conditions to itself. So I've drawn a picture which is intended to explain that. So in A, I'm trying to explain why a line operator gives a mapping from an object in the category of boundary conditions to a new object. So B is a boundary condition. Then I consider the special case where T runs along the boundary. We don't have to, it could be any embedded one manifold, but to get this statement, we take T to be living at a point in the Riemann surface C, but in sigma, it's a one manifold that runs along the boundary. And in topological field theory, there's no meaning for the distance between B and T. You could move T all the way up to the boundary, and then it defines a new boundary condition, T times B. That explains how T acts on objects of the category. The point of B is to explain how T acts on morphisms of the category. So although this is a slightly different picture from the one I explained before, you can think of a morphism as a point on the boundary that gives a junction from a boundary condition B to a boundary condition B prime. In the previous picture, the morphism is sort of another open string that joins on. But by conformal mapping, I could replace this with, I can conformally map that external open string to a point junction. So another picture of a morphism is that it gives a junction from one boundary condition to the next with some local data you have to supply at that point. And that local data is an element. Well, if you want to express these pictures in terms of categories, you say the local data defines an element of Hom from B to B prime. In any event, okay, and then here I've composed Hom from B to B prime with Hom from B prime to B double prime. But now the picture shows we could move T up to the boundary, and then we'd get a junction from TB to TB prime. So that's meant to explain that T acts on morphisms in the category. So I hope I've succeeded in explaining why a line operator behaves as a functor from the category of boundary conditions to itself. So I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn. And T really depends on the choice of a point, P, in the Riemann surface C. Such pictures make it obvious that the line operators T of P and T of P prime commute as functors on the category. You see, in a purely 2-dimensional picture, Okay, well, I've drawn a purely two-dimensional picture that describes acting on a boundary condition B with first T of P and then T of P prime. In purely two-dimensional terms, there's an ordering of the two line operators, one to the left of the other and closer to the boundary, and in general, functors would not commute. But here, T of P and T of P prime depend on the choice of points P and P prime in the Riemann surface C not drawn. And then if P is not equal to P prime, you can move the two past each other with no singularity because in 4 dimensions, they're not meeting. So you learn that T of P times T of P prime acting on a boundary condition B is the same as the two T's acting in the opposite order. That's obvious if P is not equal to P prime, and therefore it's also true by limit if P equals P prime. So the two dual categories, C and C dual, are equipped with dual families, T of P and W of P of functors, parameterized by the choice of P in C and some other data, and commuting at distinct points. So T of P corresponds to the usual Hecke functors of geometric Langlands, and W of P is its dual in the usual geometric Langlands duality. Now these functors depend on more data. W depends on the choice of a representation R of the dual group. So likewise, T depends on a choice of representation of the dual group. So you could consider two Hecke functors at the same point for possibly different representations. They still commute by a limit argument since they would have commuted at distinct but nearby points. Now the duality says that the algebra of composition of Hecke operators at the same point is the same as the corresponding algebra of composition of Wilson operators at the same point. And that, on elementary grounds, is the tensor algebra of representations of the dual group, where the tensor product of the two representations can be expanded as a sum of irreducibles. So the product of the two Wilson operators can be written as a sum of Wilson operators for irreducibles. The fact that the decomposition of the Hooft operators match that of the Wilson operators is known as the geometric Satake correspondence. So, Michael, do we usually take questions during the talk? I'm not hearing an answer, but anyway, if there are any questions, feel free to ask them during the talk. Now, to go into a little more detail, I want to introduce a useful language for formulating a simplified version of geometric Langlands duality. So let M sub H be the moduli space of Higgs bundles. So if the group is G, I'll call it M sub H of G and C, or just M sub H of G for short, where G is the gauge group, which for physicists is a compact form of the Lie group. So Hitchin showed that the Higgs bundle moduli space is a hyperkähler manifold. In one complex structure, it parameterizes Higgs bundles. In another complex structure, it parameterizes flat bundles over C, with the structure group being the complex Lie group G sub C. So the two complex structures, together with their product Ij equals K, act as the usual unit quaternions and are part of a hyperkähler structure. There also are the three corresponding Kähler forms, omega I, omega J, and omega K. So geometric Langlands duality for many purposes is a mirror symmetry between the A model of the Higgs bundle moduli space for G and the B model for G dual for particular symplectic and complex structures, which in Hitchin's notation are omega K on the symplectic side and J on the complex side. This instance of mirror symmetry was first studied mathematically in this paper. So you can definitely ask questions for which the two-dimensional picture is inadequate. Mathematicians describe this by saying that the theory should be formulated on the stack of G bundles, bun G, not on a finite dimensional moduli space. Physicists describe it by saying that the correct formulation is as a duality of four-dimensional theories. 4 is the minimum. There's a 6-dimensional formulation that explains some things better, but 4 is sufficient for a complete statement of the duality. The two descriptions by a stack or a four-dimensional gauge theory are not as different as you may think, because Atiyah and Bott showed in a well-known paper that a model of bun G is the space of all connections on a fixed smooth G bundle E over C. So four-dimensional gauge theory, which can be thought of as two-dimensional theory where the fields live on an additional two-dimensional space C, can be thought of as a two-dimensional theory with target bun G. So if you're a physicist, the talk about the stack of G bundles is just a mathematician's way to say that you really are doing four-dimensional gauge theory, not a two-dimensional sigma model. A two-dimensional sigma model is a useful approximation for many purposes, but the real statement is a four-dimensional gauge theory. Now, there's another bit of background we'll need before we try to get to Eddinghaus, Frankel, and Kazhdan. I want to use the two-dimensional description of geometric Langlands duality as mirror symmetry between the Higgs bundle modular space and its dual for the dual group to motivate the statement that the category that appears on the automorphic side of the duality is a category of D modules. So on the automorphic side, we're discussing simply the A model or Fukaya category. Well, the approximation that's best developed mathematically is the Fukaya category of this moduli space. And then the familiar A branes are the Lagrangian branes supported on a Lagrangian submanifold L. But Kapustin and Orlov discovered that to make mirror symmetry work, you have to introduce also coisotropic A branes that are supported on a coisotropic submanifold of Y that's above the middle dimension. The construction of coisotropic A branes is delicate in general, but the simplest case is the case that we need. The simplest case is that Y is actually a complex symplectic manifold with complex structure I and a holomorphic symplectic structure that I'll call omega J plus I omega K. My notation is as if Y is hyperkähler, although here I will be making a statement that doesn't really require that. Anyway, the simplest case is that we have this set up, and we're viewing Y as a real symplectic manifold with a symplectic form that's the imaginary part of a holomorphic 2 form. Then you take the B field of the sigma model to be the real part of the holomorphic 2 form. With this data, you can construct a canonical coisotropic A brane, which I'll call B sub CC, whose support is all of Y. It has the property that roughly Ham from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on Y. More specifically, you can show that if Y is a cotangent bundle of some other complex manifold, then the sheafified version of Ham from BCC to itself is the sheaf of holomorphic differential operators on W, while holomorphic operators acting on sections of K to the 1/2, where K is the canonical bundle of W. So for geometric Langlands, Y will be the Higgs bundle moduli space. It's birational to a cotangent bundle, the cotangent bundle of the moduli space of holomorphic G bundles on C. So then A will be the sheaf of holomorphic differential operators on the finite dimensional moduli space. That means also that if B is any other A brane, then Ham from B to BCC will be a D module, that is a module for the sheaf of holomorphic differential operators. So that means that the category on the automorphic side of the geometric Langlands duality will be a category of, roughly speaking, D modules on the ordinary moduli space of bundles. Now, mathematically, you should work with D modules on the stack bun G, not on a finite dimensional space. Physically, what that means is that it's important that a version of this coisotropic brane can be defined directly in 4 dimensions, not only after reducing to a 2-dimensional description. Kapustin and I had a version of that in our original paper, but Gayotto and I improved it a few years later in this paper. And that enabled us to answer a question that had been unclear physically. The answer to this question had been known mathematically, but was unclear physically, and will be important later in this lecture. What's the dual of the canonical coisotropic brane itself? So as I said, the canonical quasitropic brane is an A brane. So its dual will be a B brane, that is a coherent sheaf or a complex of coherent sheaves on the Higgs bundle moduli space of the dual group. Well, Bailenson and Drinfeld had shown mathematically what's the dual. Well, the D module corresponding to BCC itself is the sheaf of differential operators. And its dual, well, the sentence starting from here is what Bailenson and Drinfeld had essentially showed. That if you take the differential operators regarded as a D module, then its dual is the structure sheaf of the variety of O pairs, which is a very special Lagrangian submanifold of the Higgs bundle moduli space. I'll call it L sub O, the Lagrangian variety of O pairs. So a gauge theory explanation of that was initially unclear, at least to me, but Gaiuto and I found one in this paper. So I wish there was time to explain all this more, but there isn't if I want to get to the more current developments. But I'll summarize this by saying the following. The main ideas in the gauge theory geometric Langlands correspondence are the following. The first is electric-magnetic duality between the group and the dual group of supersymmetric gauge theory in 4 dimensions. Twisting to make a dual pair of topological field theories. Compactifying to 2 dimensions on a Riemann surface C. The dual pairs have dual sets of line operators with 't Hooft operators on the G side and that correspond to geometric Hecke transformations, and dual Wilson operators on the other side that correspond to representations of the dual group. On one side of the duality, there's this distinguished brane BCC that establishes a map from A branes to D modules on bun G. On the other side, one is studying B branes in the complex structure in which you're considering flat bundles with complex structure group. So these are the main ideas of the correspondence as much as I can explain it today, but I should try to stop for questions just for a moment. I assume people can unmute themselves and ask questions if they want. Is that the case, Michael?
Yeah, they can indeed.
Okay, but I'm not hearing questions. So if that is the case, I'll just go on. Well, the story as I've explained it so far involves deformation quantization, not quantization. But in proceeding, it's really important to discuss quantization rather than deformation quantization. And I want to pause to explain the difference because even though it's elementary, I do find it can cause confusion. So I'm going to consider a concrete example of a two-sphere. So here x, y, and z are simply real variables. And I consider the two-sphere x squared plus y squared plus z squared equals j squared, viewed as a symplectic manifold with its usual rotation invariant symplectic form, which we can write as simply dx dy over z, although that way to write it doesn't exhibit the rotational symmetry. In deformation quantization, we start with the commutative algebra of functions, which here you can think of as polynomials in x, y, and z, complex valued polynomials, and we want to deform it to a non-commutative algebra. In general, you specify that the leading non-commutative deformation should agree with the Poisson bracket, and then we ask if there is a family of associative algebras over C of H bar or maybe C double bracket of H bar with that property. So this would mean that you can set H bar to an actual number, and this would mean that you have to work over formal power series in H bar, and that you get a formal family of algebras, but not an honest algebra with where you can set H bar to a number like 1. So in the present case, we can just write down the answer, which is given by the SU2 algebra. So that's a family of associative algebras over a C of H bar. H bar, in other words, it makes sense with H bar interpreted as a complex number. To these relations, we should add the fact that x squared plus y squared plus z squared is j squared. Now, that's deformation quantization. It's not quantization where you would have a Hilbert space that the algebra acts on. And in this generality, quantization isn't possible because I haven't put any condition on J. which could be an arbitrary number. In fact, if we let x, y, and z be complex variables, and with complex polynomials, j could be an arbitrary complex number. But in the setup I gave for the two-sphere with its usual symplectic structure, j was an arbitrary real number. In that generality, there's no quantization. Quantization means finding a Hilbert space H, which is supposed to have the appropriate size. Its dimension is roughly the symplectic volume of the phase space that the algebra acts on. That does not exist for arbitrary j. To construct H, one has to quantize the parameter j, set it to preferred values at which the Hilbert space exists. These special values correspond to the angular momenta in the real world of electrons, atoms, molecules, and so on. So physically, x, y, and z could be the generators of angular momentum, or the angular momentum charges, conserved quantities. This is the algebra of the angular momentum generators. But in the real world, angular momentum has preferred values. It's quantized. Quantum mechanics got its name because the parameters are quantized. In deformation quantization, J was not quantized, but in quantization, where you want to Hilbert space, J is quantized to special values at which this algebra has a nice Hilbert space representation.
Question?
Yes?
So if you allowed an infinite dimensional Hilbert space, then you would not have this quantization of J. So part of the specification is that the Hilbert space be of the appropriate size.
Yes, which I didn't want to explain. So you see, if we wanted to discuss in this framework, for example, unitary but infinite dimensional representations of SL2R, we would not begin with this real orbit. We should begin with an orbit of SL2R. And my statement about the appropriate size was too crude if we're interested in the infinite dimensional case. I was trying to avoid getting to a point like that. What did I do? I somehow went to the beginning. Well, since I'm stuck trying to scroll through to the right points, this is a good moment for another question if there's one. Anyway, that's the difference between quantization and deformation quantization. And just remember, quantization got its name because the parameters are quantized, which isn't the case in deformation quantization. So Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. And the answer is yes, under certain conditions. Recall that in general, up to this point, we have a complex symplectic manifold, which in geometric Langlands would be the moduli space of Higgs bundles. But for the moment, it could be any complex symplectic manifold. And then to get deformation quantization, we viewed Y as a real symplectic manifold with the symplectic form, which is the imaginary part of the holomorphic symplectic form. And then the A model provides a framework for deformation quantization of Y. To get actual quantization, we need something more. So let's discuss Lagrangian A branes. That means branes supported on a Lagrangian submanifold of Y, a submanifold that's Lagrangian for M omega. So we're viewing Y as a real symplectic manifold with this real symplectic form. So L being Lagrangian in general just means it's Lagrangian for M omega. In many examples important in geometric Langlands, L is actually a complex Lagrangian submanifold. That is, it's Lagrangian for omega, not just M omega. For example, if you take a skyscraper sheaf on the dual side, supported on a point in the Higgs bundle moduli space, its dual will be a Lagrangian brane supported on a fiber of the Hitchin fibration. That's a complex Lagrangian submanifold. This happened because a point in a hyperkähler manifold is hyperholomorphic. It's holomorphic in every complex structure. So these branes are very important in geometric Langlands. They're the eigenbranes, the Hecke eigenbranes. Hecke eigenbranes correspond to Lagrangian branes that are Lagrangian in the complex sense. And that's because they're dual to a sheaf supported on a point in the moduli space of local systems. but a point is homomorphic in every complex structure. And that'll be dual to the fact that we actually get a complex Lagrangian brane. So some very important objects are complex Lagrangian submanifolds, but in general, for an A brane, L need not be Lagrangian for omega only for its imaginary part. Just as generically, a coherent sheaf on the Higgs bonded moduli space isn't hyperholomorphic. In fact, in usual discussions of geometric Langlands, people don't even mention the notion of something being hyperholomorphic. So in geometric Langlands, the ones that are complex Lagrangian are very important. But Gukov and I considered the opposite case of an A brane whose support M is Lagrangian for M omega, as it must be by definition of an A brane, but symplectic rather than Lagrangian for real omega. So that's the opposite case from the case I just mentioned. We argue that in this case, Hom from B to BCC represents a quantization of M with the symplectic structure real omega. See, first of all, if M is symplectic for real omega, then it makes sense to try to quantize it with that symplectic structure. And we claim that such a quantization is in fact provided by the A model of the complexification of M. So for example, if Y is an affine variety which has a lot of holomorphic functions, they're deformation quantized to get Hom from BCC to itself. For any A brane B, Hom from B to BCC will be a left A module. Well, see, if M is such a real Lagrangian submanifold of Y, that means you can view Y as a complexification of M. So holomorphic functions on Y are analytic continuations of certain real analytic functions on M. There are enough of them to get a reasonable quantum deformed algebra of observables, and that's the algebra that acts on this H. So I'm afraid I've highly compressed that, but that was how we interpreted quantization in terms of the A model. So, well, Hom from B to BCC is an A module that one can show has appropriate properties to be a quantization of M, except you need one more condition if you want it to be unitary. If you want H to be a Hilbert space, not just a vector space, that's an A module. So I've omitted a key point, which is what structure we need so that this H is a Hilbert space and not just a vector space. In general, if B1 and B2 are any two branes, there is a non-degenerate bilinear, not Hermitian pairing between Hom from B1 to B2 and Hom from B2 to B1. To get a Hermitian product is the same as finding an antilinear map from one to the other. So we showed that there's such an antilinear map, which I'll call theta tau, if Y has an anti-homomorphic map with M as a component of its fixed point set. I won't explain the definition of theta tau, but I'll explain why one should expect the existence of such a tau to be the right criterion. If holomorphic functions act on Y, act on H, and H is a Hilbert space, then there will be a notion of which holomorphic functions on Y act as Hermitian operators. Existence of tau gives such a notion. A holomorphic function on Y is real if it's real when restricted to M. So that was what we needed to define a Hermitian pairing. And given such a tau, the Hermitian product on Hom B1, B2 on any pair of tau invariant branes is defined using theta tau, the antilinear map that comes from tau, and also the bilinear pairing of the A model. So I've left out a lot of steps. I didn't explain the role of CPT. This pairing is always non-degenerate, but in this generality, it's not positive definite. And for the specific case relevant to quantization, we expect positivity because we're close to a classical limit of quantizing a cotangent bundle. So in this approach to quantization, if you're given a real symplectic manifold that you want to quantize, you have to first find a complexification of M to a complex symplectic manifold Y with some appropriate properties. And then you can use the A model of Y to quantize M. So the main property you need for Y is simply that it does have a good A model. And that's a subtle condition. So we don't know general necessary and sufficient conditions for that. We can only give sufficient conditions at a physical level of rigor. We could compare this loosely to geometric quantization, which is the closest there's been to a systematic approach to quantization. In geometric quantization, to quantize M, you have to find a polarization of M, roughly a maximal set of Poisson commuting variables. Given a polarization, geometric quantization gives a recipe of quantization. So either geometric quantization or quantization by Branes can give good results if there's a natural polarization in the case of geometric quantization, or natural choice of the complexification in the case of quantization by Branes for the problem at hand. Now, I'll say one more thing before I try to tell about the work of Eddinghoff, Frankel, and Kazhdan. A limitation in my paper with Grukov is that we didn't understand very much about comparing brane quantization to geometric quantization. Now, as I said, Gallardo and I were motivated to look at this more closely as background to understanding the work of Eddinghoff et al. At some level of precision, we were able to compare quantization by Branes to geometric quantization in the following sense. If M can be quantized both ways, in geometric quantization using a polarization P, in brane quantization using a complexification Y, then you'd like a criterion that would show that the two quantizations agree. And I'll simplify the statement slightly, but basically we showed that if P can be analytically continued to what we call a homomorphic polarization of Y, then the two quantizations agree. Geometric quantization of M using the polarization P is equivalent to brane quantization of M using Y. Now, all this is by way of preparation to talk about the work of Eddinghoff, Frankel, and Kazhdan that I mentioned at the start. But maybe I'll give you another chance for questions before I go into that. Well, if there are no takers, I hope that's not because I
Sorry, I have a question. So what exactly does it mean for the quantizations to be the same? I mean, all Hilbert spaces are isomorphic. Is there some operator algebra?
Yes, of course. There are operators that act on each side. For brane quantization, I told you what acts. And geometric quantization also gives an answer for what acts. And in this situation, they agree. So Eddinghoff, Frankel, and Kazhdan considered a Hilbert space H of L2 functions, or better half densities, on the moduli space of stable homomorphic G bundles over C. It's more natural to call them half densities, but because this moduli space has a natural measure, because it has a natural Kähler structure, you could simply call them functions. Then they constructed operators in H that are related to the usual constructions of geometric Langlands, and found interesting dualities, theorems, and conjectures concerning the action of these operators. So I really wouldn't have time to tell you what all their statements were. Rather, I'm going to proceed with the physical picture. As we proceed with the physical picture, we'll see what those statements might be. So I'll explain what they did in the context of explaining a physical interpretation of it. So in geometric quantization, you'd understand L2 functions or better half densities on M of G in terms of quantization of the cotangent bundle, T star of M of G, which is in an L2 theory, can be thought of as the Higgs bundle moduli space, MH of G. So in other words, the Hilbert space of EFK is what you get if you take the Higgs bundle moduli space MH of G with the real symplectic structure M omega and quantize it by geometric quantization using the fact that it's a cotangent bundle. So then EF and K studied natural operators on this Hilbert space and made duality statements about them.
Sorry, I have a question. So that's only, I thought those were only birationally equivalent. That doesn't matter for this?
Well, in an L2 theory, that's not going to matter because in L2 theory, you can always throw away a set of measures 0. And Birational equivalence means that they're the same except for a set of measure 0. On the other hand, if we're going to get anywhere in terms of predictions from duality, we need to understand the quantization of the Higgs bundle moduli space via Branes. Now, remember, I told you that the first step to quantize anything by Branes is to pick a complexification of it. In this case, the Higgs bundle moduli space is already a complex manifold. So we have a complex manifold which we're viewing as a real symplectic manifold, and we want to complexify it again. Well, any complex manifold viewed as a real manifold has a canonical complexification, namely y hat, which is y1 times y2, where y1 and y2 are two copies of y with opposite complex structures I and minus I. And y hat comes with an involution. I wrote u hat here, but it was meant to be y hat. Y hat comes with an involution tau that exchanges the two factors. And since the two factors have opposite complex structures, this is an anti-holomorphic involution, and it leaves fixed the diagonal. So we have the starting point of Brane quantization we get for free. Namely, we simply replace y by the product of two copies with opposite complex structure and view that as a complex manifold that has an anti-holomorphic involution that leaves fixed the original y. So as I said, the fixed point set is the diagonal in y1 times y2. Since the complex structures on the two factors are opposite, we can take the holomorphic symplectic form of y hat to be what I'll call omega hat, which is 1/2 omega on one factor and 1/2 omega bar on the other factor. So omega is the holomorphic 2 form of y. I take a 1/2 omega on one factor, 1/2 omega bar on the other factor. So that's holomorphic in the complex structure of y hat. Then the restriction of omega hat to the diagonal is real omega. In other words, the diagonal is a copy of y that's Lagrangian for m omega and symplectic for real omega. So this is the appropriate situation where the A model of y hat is appropriate for Brane quantization of y viewed as a real symplectic manifold with a symplectic structure real omega. So that's the situation in which quantization of y using a Lagrangian Brane B supported on y makes sense. Moreover, I told you that there was a certain condition under which geometric quantization agreed with Brane quantization, and that condition is satisfied here. So that sentence is meant to explain why EF and K studied the geometric quantization of y using a natural real polarization, which was part of Hitchin's description. But what I'm explaining is why geometric quantization using that real polarization is equivalent to Brane quantization in this setup here. So the Hilbert space they study is the one that would arise in Brane quantization. However, we have to ask what are the observables in Brane quantization. Let's recall Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration pi from Higgs bundle moduli space to a certain base, which is Cn for some n. The linear functions on V are Hitchin's commuting Hamiltonians. Classically, the global holomorphic functions on the Higgs bundle moduli space are just the pullbacks of functions on V. So the algebra A0 of holomorphic functions on the Higgs bundle moduli space are just the polynomial functions of the classical Hitchin Hamiltonians. What are the quantum observables in Brane quantization? Well, for Brane quantization, we define the canonical quasitropic brane of y hat, which is y1 times y2. It's just a product of canonical quasitropic branes for the two factors. So the algebra that will act on quantization is just a product A tensor A bar, where A is A is the same thing for canonical quasitropic brane of y1 and A bar for y2. The quantum deformed versions of A0 and A0 bar, the holomorphic and anti-holomorphic functions on y. However, for the Higgs bundle moduli space, you can show that the quantum deformed rings are still commutative. That's due to Hitchin for SL2 and to Balanson and Drinfeld for in general. And Kapustin and I also gave a gauge theory explanation. So the quantum deformed objects are the commuting differential operators, which are the quantization of Hitchin's classical commuting Hamiltonians. So we want to understand the action of A tensor A bar on the Hilbert space, which, because of the equivalence to geometric quantization, is the same as the half densities on the ordinary moduli space. First of all, there's no mystery about the fact that A tensor A bar does act on the Hilbert space. That's just the statement that holomorphic and anti-holomorphic differential operators can act on functions on the moduli space. Well, better here half densities, but it comes out to be the same. Holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic and anti-holomorphic differential operators are separately commutative. So there's no mystery about the fact that A tensor A bar acts on the Higgs bundle moduli space as a family of commuting operators. But what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we want to apply duality. To apply duality to Ham from B to BCC, where BCC is the product of the two quasitropic branes and the two factors, and B is the Lagrangian brane of the diagonal, we need to understand the duals of the three branes involved. So these two are the branes associated to the ring of holomorphic functions and anti-holomorphic functions for the other one. And as I explained before, the dual is the structure sheaf of the variety of O pairs. An O pair is a flat bundle whose holomorphic structure obeys a certain condition that I will recall in a few minutes. And BCC2 is similarly related to deformation quantization of the ring of anti-holomorphic functions. So its dual is the structure sheaf of what I call L O pair bar, the Lagrangian submanifold that parametrizes flat bundles whose anti-holomorphic structure obeys the O pair condition. What about the brane B supported on the diagonal? There's an unfolding trick that shows we don't have to worry about it. So we had two copies of the A model of Y that were totally decoupled, except that the brane B was supported on the diagonal. So think of each of the two copies as living on a strip, but the two strips on one boundary are glued together by the fact that the boundary condition says that the two boundary values are equal for the two theories. If I unfold it, I just have a single theory on a strip of twice the width, with BCC1 on the left, BCC2 on the right. I've drawn the diagonal line here in the middle of the strip, but nothing's happening there. Because the boundary condition just said that the boundary values on the two sides were equal there, and you can just forget about it in this picture. The boundary condition just says that the fields are continuous in the middle, which is what you'd have assumed if you just erased that line. In the unfolded picture, there's just a single copy of the Higgs bundle moduli space, and the Hilbert space is Ham from one quasitropic brane to the other, where BCC is the quasitropic brane for one complex structure, and BCC tilde is adapted to the opposite complex structure on the same space. But they're both A branes in the same A model of the same space. So now we can easily dualize this. The dual of BCC is a Lagrangian brane, and the dual of BCC tilde is another Lagrangian brane, namely the variety of O pairs and the variety of anti-holomorphic O pairs. So A becomes Ham from L O pair to itself. That's just the algebra of holomorphic functions on L O pair, according to a celebrated result of Balanson and Drinfeld. And A bar, likewise, is the holomorphic functions on L O pair bar. So here are the two dual pictures. In one picture, you have a strip with the two quasitropic branes on the left and right, and this is in an A model. The other picture is a B model picture, and there's simply two Lagrangian branes on the two sides. So, okay. two branes that are supported on complex Lagrangian submanifolds on the two sides. And the Hilbert space is Hom from B tilde C. The Hilbert space in one case is Hom from here to here, but in the other case, it's just the intersections in the B model of two Lagrangian branes. And the intersections in the B model are simply supported on the physical intersections between the two Lagrangians. So LO pair and LO pair bar are Lagrangian branes. So Hom from one to the other is an intersection space. Actually, what is written here is wrong. It's just a B model intersection space, which is more simple than a statement in fluoric homology. So here I've written a slide that elaborates upon the fact that the variety of O pairs and also the variety of complex conjugate O pairs are complex Lagrangian submanifolds in the same complex structure. That's because we're looking at the Higgs bundle moduli space and the complex structure in which it parameterizes flat bundles over with the structure group being the complex Lie group. The flat bundle has both a homomorphic structure and an anti-homomorphic structure. And a condition on the homomorphic structure or on the anti-homomorphic structure, either one is a homomorphic condition from the point of view of the moduli space of flat bundles. Now, as I explained before, using the existence of the homomorphic involution tau, Hom from B tilde CC to BCC carries a Hermitian inner product, which we expect to be positive. The dual space likewise carries a non-degenerate inner product, which is defined in a similar way using the anti-homomorphic involution of the dual moduli space. But the positivity on the dual side is very subtle. For generic B branes, the non-degenerate inner product that you define is not positive definite. The conditions that make the Hermitian form positive were defined by Eddinghoff et al., who showed these conditions are satisfied for GL1 and for SL2. So if you let X be a point in LO pair intersect LO pair bar, it corresponds to a flat bundle E. That's an O pair both homomorphically and anti-homomorphically. The anti-homomorphic involution that's used to define the Hermitian structure will map E to the complex conjugate flat bundle E bar, which is also an O pair both homomorphically and anti-homomorphically. If E isn't isomorphic to E bar, then they're both null vectors for the Hermitian form, which in that case is not positive definite. But the duality predicts that it should be positive definite, so we expect that as conjectured by EFK and proved in some cases, E is always real, that it's always isomorphic to E bar. So the claim is that flat bundles with complex structure group, this should be for the dual group, that are O pairs both homomorphically and anti-homomorphically, are actually real. That is, their structure group reduces to a real form. You can also show that positivity requires that the intersection points should be transverse. And that's also among the results and conjectures of EF and K. So a flat bundle that's an O pair homomorphically and anti-homomorphically and is also real is what they call real O pairs. So the claim is that the real O pairs correspond to the intersection points. And therefore, the joint spectrum of A and A bar corresponds to real O pairs. Recall that according to Balanson and Drinfeld, an element X of the algebra of homomorphic functions has two interpretations. It's a homomorphic differential operator on Bungie, the moduli space of bundles, and it corresponds to a homomorphic function, f sub x, on the variety of O pairs. Similarly, an element of the corresponding anti-homomorphic algebra is an anti-homomorphic differential operator on the same space, and it corresponds to a homomorphic function, fx prime on the variety of anti-holomorphic ogres. So an intersection point P of the two Lagrangian branes determines a pair of eigenvalues for the differential operators x and x prime, namely fx of P and fx prime of P. And that's the proposal for the joint spectrum of Hitchin's quantized Hamiltonians. Now, in all versions of Langlands correspondence, it's also very important to consider the Hecke operators. So EF and K introduce Hecke operators as operators on the Hilbert space H that arises in quantization of the Higgs bundle moduli space as a real symplectic manifold. I already explained that line operators of the four-dimensional gauge theory can be used to define functors on the category of branes. And that Houghton-Wilson line operators are dual pairs of functors. The same line operators represent operators on the quantum Hilbert space. I've tried to explain this with a picture. So before we had a line operator running along the boundary, it was a functor on the category of branes. The same line operator running from left to right defines an operator on quantum states. A quantum state goes in at the bottom after interacting with the line operator, comes out as a new quantum state at the top. So T has acted simply as a Hilbert space operator, an operator on quantum states. The next picture was aimed to explain what happens at the endpoints. There's some important structure at the endpoints in B, but I won't have time to explain that today. Now, the argument that showed that the functors corresponding to line operators commute for different points goes over immediately to show that line operators viewed as ordinary operators on quantum states also commute. It's simply the same, basically the same argument as before. Because they live at different points in C, they can be moved up and down in this picture without singularity. And moreover, as in the previous case, we can consider the case that P equals P prime as a limiting case. And a similar argument shows that Hecke operators, viewed as operators on quantum states, commute with the quantized version of Hitchin's holomorphic or anti-holomorphic Hamiltonians. In a two-dimensional picture, it looks like there could be a problem in sliding an element of A represented as a local operator on the boundary past a Hecke operator TR of P. But in 4 dimensions, it's obvious there's no problem because X can be assumed to have support disjoint from T. Finally, we should ask what are the predictions of the duality for the eigenvalues of the Hecke operators. To answer this, we start on the dual side. We're going to find the eigenvalues of a Wilson operator acting on Ham between the two Lagrangian branes, and then the duality will predict the eigenvalues of the Hecke operators. Also, we'll find what kind of data is needed for the corners that make the Wilson operator to be an operator. Again, the duality predicts that the same data is needed to define the Hecke operator. So I now have to tell you what is a Wilson operator. If we have a G bundle E and we're given a representation of G, then we can form an associated bundle E sub R. And if G had a connection, then E sub R also comes with a connection. The corresponding Wilson operator for a path in our 4 manifold is defined by parallel transport of the connection along the path gamma. For the present application, we fix a point P and C, and we fix 2 points A and B on the left and right boundaries, and a path in sigma times P from A times P to B times P. So everything happens at a fixed point P inside C, but in sigma, we have a strip and a path from A times P to B times P. And we take the holonomy operator from left to right. Well, in general, the holonomy operator along a path with endpoints is not a number. A holonomy is a linear transformation from the fiber at one endpoint to the fiber at the other endpoint. Now, I want to state this more symmetrically, so you can consider the holonomy to be a homomorphism from one fiber times the dual of the other fiber into C. The dual of the other fiber is the fiber for the dual representation. Now, a quantum operator will come from a complex valued function of connections, which this isn't. This is a linear function on a vector space, not a function. We don't have that yet. So far, we have a linear operator from a natural vector space to C. To get an operator, we have to supply elements in the two vector spaces. And then this linear transformation applied to the tensor product of the two vectors will be a function, a complex number depending on the data. Its quantization will be an operator. To avoid unnecessary details, I'll take the dual group to be SL2, and I'll take the two representations to be the two-dimensional representation. But there is a straightforward generalization to any group and representation. So in this picture, the boundary condition on the right boundary is that the G-dual bundle E is an anti-holomorphic opair on the right boundary. And that means by definition, and here I will finally give you the definition of an opair, that there is an anti-holomorphic non-split exact sequence where K bar is the canonical bundle of C with opposite complex structure. K bar to the 1/2 is a square root. So we pick a vector in K bar to the 1/2, and that gives a vector J bar of V in the fiber at the left. Similarly, on the right, the bundle is a holomorphic opair, so there's a non-split exact sequence. So we pick a vector W in K to the 1/2, and that gives us J of W in the appropriate fiber. So once they're picked, we can apply the W that we had before, which was a linear transformation, to the vector J bar of V tensored with J of W. And that's the complex valued function of connections that we want to interpret as a quantum operator. That step is trivial because in the B model, because an opair is irreducible as a flat bundle, we can actually assume that the connection is pulled back from C up to a possible twist by an element of the center. So that means parallel transport from left to right does nothing, except possibly multiplied by an element of the center, which for the case that G dual is SL2 is plus or minus 1. So up to sign, W hat is just the dual pairing between the two fibers, which are simply two different ways of looking at the same flat bundle. And so the eigenvalue of W hat for this particular intersection point is just plus or minus the pairing in the two-dimensional representation between the two vectors we had. And therefore, the duality predicts that the eigenvector of the 't Hooft operator, well, first of all, that defining it requires the same data. And secondly, that the eigenvalues of the resulting 't Hooft operator are the same as we found on the dual side. So I probably zoomed through that a little bit too fast, but I hope to have given you at least a sense that the dual of the question of finding the eigenvalue of an 't Hooft operator is a problem that has a classical answer on the B model side. And having found that answer, that's going to be the prediction for the eigenvalue of the 't Hooft operator on the A model side. Thank you.
Thank you very much, Edward. Maybe we should begin with see if there are any questions for you, and then open the discussion more generally to the whole, to the other speakers. Greg.
Yeah, I had a question about the commuting differential operators A on L2 of M of G.
Yes.
So is that the center, the same as the center of the universal enveloping algebra and affine Lie algebra at the critical level? So does it have WZW interpretation?
Well, first of all, what you've just said is how Bailenson and Drinfeld prove the commutativity for general groups. Hitchin kind of did it for SL2 by a special case of that. Secondly, there is a natural way of looking at the physics that naturally leads to that construction, to that interpretation. It was developed in some of David Goethe's work in the last 4 or 5 years. So yes, there is, not only is there that interpretation, but that was the original interpretation by Balanson and Drenfeld.
So can you explain the connection to WZW theory?
Well, it's not, the critical level is pretty weird in terms of WZW theory. So it's not anything close to a physical WZW theory.
Right, but I mean, it's always been a mystery to me. So I was wondering if this point of view.
I'm reluctant to get it. Nothing I've said in this lecture sheds any light. Your question has been elucidated in previous papers by David. I'm a little bit worried about giving a detailed answer as it gets too far from my actual lecture. But the basic idea is that corners support chiral algebras in this story. There's something important that I didn't explain in the lecture, which is that the twist in 4 dimensions gives a 4-dimensional topological theory. But we used in the lecture branes that were only topological in a 2-dimensional sense. They depended on the actual choice of the Riemann surface C. And so if you like, they were holomorphic topological branes. And if you take a corner between 2 holomorphic topological branes, they tend to support chiral algebras that live on the corner. That's the theme in a whole series of papers David wrote, some with different co-authors. And your question gets at that series of papers, really, rather than what I've done or what I've talked about today. I'm kind of reluctant to say more. It's a little bit hard to say more in a useful way.
Okay, yeah, I know what papers you're talking about. Thank you.
Any other questions? So Daniel, I think Daniel is going to lead the discussion now for the time being. Daniel, are you there?
I'm here. Thank you. Okay, thanks a lot for this very nice talk.
I guess I'll unshare if we're going through a general discussion.
Yes, thanks. So we had this breakout room session yesterday that was very successful, and we're going to do that today again. But it was suggested that we actually take maybe 15 minutes to allow for everyone here in the main room to ask some questions to all of the speakers, because there wasn't really much time for questions during the talks. So we will just see how that goes, and I will allow anyone to unmute themselves and ask questions to the speakers. I think both Boris and Eric are present, and at least Jens Funke and Steve Miller are present from yesterday. So yeah, please, if there are questions, go ahead.